SQL queries can also be nested. In other words, complete select from blocks can appear in the work class of another query. The subquery or inner block is nested in the outer block. Multiple levels of nesting are allowed. Typically, the query optimizer will start by executing the query in the lowest level inner block. Let's work out some examples. Assume we want to find the name of the supplier where a purchase order with number 1560 is placed. We need data from two tables, supplier and purchase order. We can now formulate a nested SQL query as follows. Select subname from supplier where subnumber equals select subnumber from purchase order where purchase order number equals 1560. To solve this query, the query optimizer will first solve the inner block, which is select subnumber from purchase order where purchase order number equals 1560. The result of this inner block is 32, which is a scalar. That's why this is sometimes also referred to as a scalar subquery. We can now solve the outer block query, which becomes select subname from supplier where subnumber equals 32. The result of this query is best wines. Subqueries allow to solve queries in a step-by-step sequential way. They may provide an interesting alternative to joins. In our example here, the question could also be easily solved with a simple inner join. Consider the following question. Retrieve product number and name for each product that exceeds the available quantity of product 178. We only need one table to solve this question, product. The nested SQL query becomes select prod number, prod name from product where available quantity is strictly bigger than select available quantity from product where prod number equals 178. The inner block is solved first. Select available quantity from product where prod number equals 178. This is again a scalar subquery resulting into the scalar 136. The outer block now becomes select prod number, prod name from product where available quantity is bigger than 136. You can see the result of this at the bottom of the slide. The where component of an outer select block can contain an in operator followed by a new inner select block. Let's say you want to retrieve all supplier names who can supply product 178. To solve this question, we need data from the supplier and supplies table. The nested SQL query becomes select subname from supplier where subnumber in select subnumber from supplies where prod number equals 178. Again, the inner block is solved first, which is select subnumber from supplies where prod number equals 178. The result of this inner block is no longer a scalar, but a multiset of values, being in our case 21, 37, 68, 69, and 94. The outer block can then be evaluated, which now becomes select subname from supplier where supplier number in 21, 37, 68, 69, 94. This query then results in the supplier names depicted. As already mentioned, multiple levels of nesting are allowed. Assume we want to retrieve all supplier names who can supply at least one type of rosé wine. This can be solved using a query with two subqueries, as you can see here. To execute this query, the RDBMS will start at the lowest level of nesting. So it will first solve the subquery, select product number from product where product type equals rosé. This will result in the values 119, 289, and 668, which are the product numbers of rosé wines. The second subquery then becomes select subnumber from supplies where product number in 119, 289, 668. The result of this subquery is 21, 21, 21, and 68. Finally, the outer block can now be evaluated, which results into deli wines and the wine depot. Note that this query can also be solved using an inner join across the tables supplier, supplies, and product. Here is another example of a nested query. We are interested in finding the product names that both supplier number 32 as well as supplier number 84 can supply. To solve this query, we need information from both the product and supplies table. The nested SQL query becomes select product name from product where product number in, select product number from supplies where supplier number equals 32, and product number in, select product number from supplies where sub number equals 84. We now have two subqueries at the same level. In a parallelized environment, both subqueries can be executed in parallel, which allows to speed up query execution. The result of the first subquery is 154, 474, 494, 657, 760, and 832. The result of the second subquery is 185, 300, 306, 347, 468, 494, 832, and 915. Since the results of both subqueries are combined using a Boolean AND operator, only the numbers 494 and 832 remain, which correspond to product names Veuve Clicquot and Conde de Hervias, respectively. In all previous cases, the nested subquery in the inner select block could be entirely evaluated before processing the outer select block. This is no longer the case for correlated nested queries. Whenever a condition in the work clause of a nested query references some column of a table declared in the outer query, the two queries are said to be correlated. The nested query is then evaluated once for each tuple or combination of tuples in the outer query. Let's give some examples. Assume we want to retrieve the product numbers of all products with at least two orders. This is a very simple question at first sight. We need data from two tables, product and PO line. The question can be solved using the following correlated SQL query. Select p.product number from product P, where 1 is strictly less than select count star from PO line, POL, where p.product number equals POL.product number. Here, we can again see a nested query. As previously, the RDBMS will start by evaluating the inner select block, which reads select count star from PO line, POL, where p.product number equals POL.product number. Unfortunately, this subquery cannot be evaluated as such, since the variable p and thus p.product number is not known here. This is an example of a correlated query, since the inner block refers to table P, which is declared in the outer block. The RDBMS will solve this correlated query as follows. it will iterate through each product tuple of the product table declared in the outer block, and each time evaluate the subquery for the given tuple. Let's give an example. Here you can see the product table depicted to the left. Remember, the tuples in the table are not ordered. The first product has product number 212. The subquery will now be evaluated with this product number. In other words, it becomes select count star from PO line POL, where 212 equals POL.prop number. The result of the subquery is 3, as you can see in the PO line table to the right. Hence, since 3 is strictly bigger than 1, the product number 212 will be reported in the output. This process is then repeated for all other product numbers, 289, 154, 295, etc. Basically, a correlated SQL query allows to implement a looping mechanism by looping through the subquery for each tuple of the table defined in the outer query block. Correlated queries allow to answer very complex questions, such as the following. Retrieve number and name of all the suppliers who can supply a product at a price lower than the average price of that product, together with the number and name of the product, the purchase price, and the delivery period. Let's read the query twice, so as to fully understand its semantics. Retrieve number and name of all the suppliers who can supply a product at a price lower than the average price of that product, together with the number and name of the product, the purchase price, and the delivery period. The query needs information from 3 tables: supplier, supplies, and product. We can now start formulating the query as a join query by using the primary foreign key relationships as join conditions as follows. Select r.subnumber, r.subname, p.prop number, p.prop name, s1.purchase price, s1.deliv period. From supplier R, supplies S1, product P, where r.subnumber equals s1.subnumber and s1.prop number equals p.prop number. We also need to make sure that the price of the product is lower than the average price charged by all other suppliers for the same product. This can be accomplished by adding another condition and a correlated subquery as follows. S1.purchase price is strictly less than select average purchase price from supplies S2, where p.prop number equals s2.prop number. You can see that the subquery refers to the product table P, which has been defined in the outer select block. It will thus be evaluated for every product tuple separately. Here you can see a visual representation of the query's functioning. Note that we use 2 appearances of the supplies table, S1 in the outer block and S2 in the correlated inner block. You can see here that product number 178 can be supplied by supplier number 37 at a price of 16.99, which is clearly lower than the average of the other prices charged by the other suppliers for product number 178. Let's now assume that we are interested in finding the 3 highest product numbers. This can be easily accomplished using an order by clause, although this solution will list all product numbers, which may not be that handy in case you have lots of products. A correlated query may provide a better solution as follows. Select p1.prop number from product P1, where 3 is strictly bigger than select count star from product P2, where p1.prop number is strictly less than p2.prop number. Essentially, this query counts for each product the number of products with a higher product number. If this number is strictly smaller than 3, the product number belongs to the 3 highest product numbers and will be reported. Put differently, there is no product with a product number higher than the highest product number. There is only one product number which is higher than the second highest product number, and two product numbers which are higher than the third highest product number. The result of this correlated query are the product numbers 915, 977, and 900. Here you can see the query illustrated. The inner query block will be evaluated for each product number separately. For product number 119, which happens to be the smallest product number, the inner query becomes select count star from product P2, where 119 is strictly less than P2.prod number. The result of this query is 41, which is clearly not smaller than 3, and consequently no output will be given. For product numbers 900, 915, and 977, the inner block will yield 2, 1, and 0 respectively, which are all less than 3, hence these product numbers will be output. Besides the in operator, which we already discussed, the any and all operators can also be used to compare a single value to a multiset. The comparison condition, small v, strictly bigger than all, big V, returns true if the value small v is greater than all the values in the multiset big V. If the nested query doesn't return a value, it evaluates the condition as true. The comparison condition, v, strictly bigger than any big V, returns true if the value small v is greater than at least one value in the multiset big V. If the nested query doesn't return a value, it evaluates the whole condition as false. Note that the comparison condition equals any is hence equivalent to the in operator. Consider the following question. Retrieve the names of the suppliers who charge the highest price for the product with product number 668. It is obvious that this query needs information from both the supplier and supplies table. It can be solved using a nested query with the all operator as follows. Select subname from supplier, where subnumber in, select subnumber from supplies where product number equals 668 and purchase price is bigger than or equal to all, select purchase price from supplies where prod number equals 668. The query has two levels of nesting. First, we start with the deepest level of nesting and execute the subquery, select purchase price from supplies where prod number equals 668. The result of this subquery are the prices 6 and 6.99. The next subquery then becomes select subnumber from supplies where product number is 668 and purchase price is bigger than or equal to all 6.99. The result of this subquery is 68. We can now finally evaluate the outer select block, which becomes select subname from supplier where subnumber in 68. The end result will then be the wine depot. Here you can see the functioning of the query once more visualized. You can see that the wine depot, which is supplier number 68, can supply product number 668 at the price of 6.99, which is higher than or equal to all other prices, in this case 6.99 and 6. Assume we have the following question. Retrieve number, name, cities, and status for each supplier who has the highest status of all suppliers located in the same city. The SQL query becomes select r1.subnumber, r1.subname, r1.subcity, r1.substatus from supplier r1 where r1.substatus is bigger than or equal to select r2.substatus from supplier R2, where R1.subcity equals R2.subcity. This is an example of the ALL operator in combination with a correlated query. It is quite self-explanatory, since it selects the supplier number, name, city, and status of a supplier R1, where the status is higher than or equal to the status of all suppliers R2, which are located in the same city as supplier R1. Let's now also illustrate the any operator. Suppose we want to retrieve the names of the suppliers who do not charge the lowest price for product 178. This can be solved with the following SQL query. Select subname from supplier where sub number in. Select sub number from supplies where product number equals 178 and purchase price is strictly bigger than any. Select purchase price from supplies where product number equals 178. This is a double nested query, and we can start again with the lowest level subquery, which is select purchase price from supplies where product number equals 178. The answer to the subquery is the multiset with elements null, 16.99, 17.99, 16.99, and 18. The next subquery then becomes select subnumber from supplies where prod number equals 178 and purchase price is bigger than any null, 16.99, 17.99, 16.99, 18. Remember, the any operator returns true if the purchase price is greater than at least one value in the multiset. The result of this query then becomes 68 and 94. The outer select block can now be run, which will give the supplier names, the wine depot, and the wine crate. The exists function is another handy construct in SQL. It allows to check whether the result of a correlated nested query is empty or not. The result is a Boolean value, true or false. In general, exists returns true if there is at least one tuple in the result of the nested query, and it returns false otherwise. Vice versa, the not-exist function returns true if there are no tuples in the result of the nested query, and it returns false otherwise. Because the exists function only evaluates whether or not a nested query outputs any rows, it is unimportant what is specified in the select component. Hence, one commonly uses select star for the subquery. Consider the following question. Retrieve the names of the suppliers who can supply product number 178. This question can be easily solved by using either a join or a nested subquery as we discussed before. Here, we present a third alternative using the exists function as follows. Select subname from supplier R where exists, select star from supplies S where R.subnumber equals S.subnumber and S.prod equals 178. You can clearly see that the subquery is correlated as it refers to the supplier table R defined in the outer select block. For each supplier, the correlated subquery will be evaluated. As soon as it returns a result, the exists function will evaluate to true and the supplier name will be reported. You can see the result of this query displayed. The exists function allows to ask very complex questions such as the following. Retrieve name, address, and city for each supplier who can supply all products. This question can be solved using a double correlated query with two no-exist functions as follows. Select subname, subaddress, subcity from supplier R, where not exists, select star from product P, where not exists, select star from supplies S, where R.SUB_number equals S.SUB_number and P.PROD_number equals S.PROD_number. Basically, this query looks for all suppliers for whom there exists no products they cannot supply. Remember, the NotExist function evaluates to true if the subquery does not return a result. This query starts from a specific supplier and then looks for all products that the supplier cannot supply. If there exist no products the supplier cannot supply, then it means that he can supply all products and the supplier name will be reported. In our example, the result of this query is null, as there are no suppliers who can supply all products. Besides the where component, subqueries can also appear in the select or from component. Here you can see a first example. Assume that we want to retrieve the product number, name, and total ordered quantity of each product, even if a product has no outstanding orders. We have solved this earlier using an outer join, remember. An alternative is the following query. Select P.PROD_number, P.PROD_name, select some quantity from PO line poll, where P.PROD_number equals POL.PROD_number as total ordered from product P. In this query, we have a subquery in the select component. This subquery will result into a scalar representing the total ordered quantity for a specific product. As with the outer join, in case no match can be found in the PO line table, a null value will be generated for the sum quantity expression. This is the case for product number 523, as you can see displayed. Subqueries can also appear in the from component. Consider the following question. Retrieve all numbers of products where the difference between the maximum and minimum price is strictly bigger than 1. This can be solved as follows. Select m.PROD_number, m.MINPRICE, m.MAXPRICE from, select prod number, min purchase price as min price, max purchase price as max price, from supplies group by prod number, as m, where m.MaxPrice minus m.MinPrice is strictly bigger than 1. You can see that the from component has a table subquery which calculates the minimum and maximum price for each product. He uses a group by clause to accomplish this. The subquery assigns the aliases min price and max price to the corresponding columns and the alias m to the overall result. These can then be used in the outer query as you can see illustrated. The result of this query are the product numbers 300 and 347. Standard SQL also supports set operations such as union, intersect, and except to combine the results of multiple select blocks. The result of the union operation is a table that includes all tuples that are in one of the select blocks or both. The result of the intersect operation is a table that includes all tuples that are in both select blocks. The result of the except operation is a table that includes all tuples that are in the first select block but not in the second. Duplicate tuples are by default eliminated from the result unless the all operator is added. Note that not all commercial RDBMSs support these set operations. Consider the following question. Retrieve number and name of suppliers who are located in New York or who can supply product number 915. This query can be solved as follows. Select subnumber, subname from supplier where subcity equals New York, union. Select r.subnumber, r.subname from supplier R, supplies S, where r.subNumber equals s.subNumber and s.prod_number equals 915, order by subname ascending. Observe how the results of both queries are combined using the union operator. To successfully accomplish this, both select blocks should be union compatible in the sense that they ask for the same columns. The final result is also sorted by supplier name by adding an order by clause to the end of the last select block. Assume that we change the query as follows. Retrieve number and name of suppliers who are located in New York and can supply product number 915. Both select blocks then remain the same, as you can see illustrated, but are now combined with the intersect instead of union operation. Note that the intersect operator is not supported in MySQL. To conclude, consider the following question. Retrieve the number of the suppliers who cannot supply any product at the moment. So in other words, retrieve the number of the suppliers who could not supply any product at the moment. This can be easily solved using two select blocks combined with an except operation as follows. Select subnumber from supplier, except select subnumber from supplies. This query selects all supplier numbers which appear in the supplier table, but not in the supplies table. Again, note that the except function is not supported in MySQL. We hereby conclude the discussion of the SQL SELECT construct to retrieve information from a relational database.